the project that I decided to do was to investigate how different algorithms were able to solve the game of Go, and the main algorithm that I decided to focus on was the Monte Carlo tree search. So, just a bit of background on the game that I decided to work on was the game of Go, which is a very old board game, which is a lot more difficult for computer algorithms to be able to solve compared to other games like chess, where you're able to use algorithms like alpha beta tree search fairly effectively, along with other techniques to be able to actually play at a high level. But for this game, they're a lot harder to even be able to solve for just a beginner or intermediate approach. I also decided to have a look at different types of reinforcement learning models after I created a Monte Carlo tree search, and then just comparing how they are able to work as well. And the main motivation that I had on it was that during college I had different classes where I was implementing AI, and I wanted to be able to make an IA that was able to work for a more difficult case and see how effectively it would be able to solve that position. The main objectives that I wanted for this project was to have a working implementation of the Monte Carlo tree search for the game, and then also compare it against the alpha beta tree search. And for the alpha beta tree search, to make it more even, I gave both of the algorithms a time limit for how long they'd have to solve each move, because for the larger boards the alpha beta would take too long if I was to just leave it without a time limit. So just adding that in makes it a lot quicker to be able to actually get it to work. And then for the Monte Carlo tree search, I implemented it so that it would have as little knowledge about the game as possible, so that the algorithms were being based off of how quickly they are able to evaluate the position and how many different positions they are able to look at just on their own. And to do that, they both have their own evaluation function. And then after that, I used a DeepQ learning model as well as a PPO model to see how well reinforcement learning would be able to work for the project. So the Monte Carlo tree search, the good thing about that is that it's able to be interrupted at any time, so that if you only have a certain amount of time in a project for it to be able to get a move, you're able to interrupt it at any time, and it'll give you at least some move. Even if it's not the best one, it'll give you the best one that it was able to find by that time. And it's also relatively good for how much memory it's able to use up, so it doesn't take up too much memory, and it's able to quickly go through the search space as it uses exploration versus exploitation to make sure it only looks at the most important moves, while also still making sure to go through different possible moves when it thinks that there might be better moves possible. Alpha beta tree search was the algorithm that I decided to use for a more traditional algorithm, as this algorithm is a lot older than the Monte Carlo tree search, so it's also used in a lot more areas. But the problem with it is that it has a problem with scaling up to a scenario where there's a large branching factor. So it's quite good if you only have a low branching factor but a large amount of nodes, because you're still able to prune a lot of the branches for alpha beta tree search. But with a large branching factor, it's not able to do that quite as effectively, so it still has to go through a lot of different board states before it's able to find the best move. And the reason why I decided to use that instead of Minimax is that it is faster than Minimax while also still giving the same move, so there wasn't much point just using the basic version of it. For DeepQ learning, it's quite a good reinforcement learning model that you can train on it just doing the games itself, so you don't have to go spend time creating a large amount of input data for it to be able to train off of. You can get it to train against itself, and then it'll use a neural network to update the Q values, so it's a lot better than the just regular Q learning in that it's able to adapt to different positions more easily. But the main problem with it is that it can take a large time for it to be able to train properly. For proximal policy optimization, it's a bit better than DeepQ learning in terms of the amount of time that it takes to actually train, and that you can do a lot of training sessions, smaller training sessions over a period of time, and then it'll still be able to learn. And even if it gets a large variety of different positions, it won't massively affect what it's already remembered, as the actual model will not be massively changed depending on the input that it gets. So for the main ways that I decided to rank each of the algorithms for the Monte Carlo tree search and the alpha beta tree search, I made a custom environment which I then had them play against each other on a couple different sizes of boards with different time limits as well. And then I kept track of how much territory and captures each of the algorithms made, as well as how long each of them took, with how many moves they are able to evaluate to see how much they are actually able to search through in the position. And that what I found was that the Monte Carlo tree search performed a lot better, especially for the bigger boards where the alpha beta tree search didn't have enough time to actually go through each of the moves. But if the alpha beta tree search was given enough time to figure out a move, it would eventually find the best move into position, as long as you have a good evaluation function. So this is the amount of moves that the alpha beta was able to figure out on a 5x5 board, and for that it was pretty much able to find the maximum number of moves. As it continues on during the game, it finds less and less as there's less available moves for it to do, so there's not as much available. But then once it moves up to the medium board, it's only able to go through 2 moves until closer to the end of the game, where there's a lot less moves, so it's able to actually calculate them more, as for each move there's a lot less that it has to evaluate before it gets to an end state or the max depth. And then for the Monte Carlo tree search, this is again the same for the 5x5 board, is that it's able to go through the max number of moves for each of the moves in a game. And then for the larger board, it still has a bit of time before it's able to fully search through the moves, but it starts off with a way higher amount of calculated moves, and it reaches its maximum a lot sooner as compared to the alpha beta search. And as well as for the amount of territory and captures, the left hand graph is for the Monte Carlo, and then the right hand graph is for alpha beta, and you can see that the Monte Carlo has a lot more captures, and especially captures, but territory as well. And then for PPO versus DeepQ learning, I trained the PPO model for around 32 time steps, and it was able to get to approximately the same level as the somewhere between the alpha beta search and the Monte Carlo search, so it was able to do quite well. And then for the DeepQ learning, I had it play on 600 games, where each game had 500 steps, which took around 5 or 6 hours to train. But at that stage, it was still making a lot of invalid moves, so for the DeepQ learning, it would need some way of being able to be told what possible moves it was able to play first, instead of just having to learn that for itself. Either that, or I need a lot more games for it to train on, which could take quite a long time for the DeepQ learning to play. And for the conclusion, the Monte Carlo tree search is a lot better compared to alpha beta when you have a large search space, as well as branching factor, as it's able to go through a lot more moves more quickly, and it doesn't need to compute as much. And I found that the PPO was better suited for Go as well, since it was able to train a lot quicker. But if DeepQ learning was given the time and I had a better model for it, then I think that DeepQ learning might be able to train better with the time given. As well as the fact that both the PPO and the DeepQ learning, once they are trained, they are both a lot quicker to actually pick a move in a given situation. It was nearly instant compared to Monte Carlo tree search or alpha beta, where it could take a few seconds if there's a time limit, or even a few minutes if you just let it go through as much as possible. And that's all of my project, and thanks for listening.